Hello and welcome to Set Theory, a bite-sized lecture series. In these videos, you'll get a conceptual overview of set theory that doesn't take all day. If you're new to this channel, be sure to check out the playlist with all the videos in this series, which I'll link to in a card in the corner of the screen. Regrettably, we have reached the end of this video series, but before we finish out the year, the last topic we're going to talk about is ordinals. Remember that in Lesson 8, we learned about cardinals, aka the size of sets. Well, ordinals are sort of like a version of cardinals that we use to talk about all the different sizes of infinity. But unlike cardinals, we don't really tend to talk about them in terms of size. Rather, different infinite sets have different orders or order types, ordinal numbers, which are sort of like classifications of sizes. Because, as we know from regular math, you can't really talk about the exact number of elements that are in an infinite set, but you can talk about what it looks like and what kinds of other sets it's similar to. Before we dive into the math of ordinals, we first have to understand something called isomorphisms. Isomorphisms are similar to equinumerosities, which we covered in Lesson 8, but they're a bit more specific. Take the natural numbers n and the integers z. If we were to draw these two sets, the natural numbers would look like this, and the integers would look like this. By our rules of equinumerosity, we can reorder z into 0, 1, -1, 2, -2, etc., or really any other way, to prove that n and z are equinumerous. They are the same size. But in order for two sets to be isomorphic, it's not good enough for them to be the same size. To oversimplify a little bit, the two sets must not only be the same size, but they must also be the same size when ordered the same way. Officially, we define an isomorphism as such. Consider structures AR and BS. A structure AR just meaning a set A, which is ordered by some relation R. So we have two sets A and B, where A is ordered by the relation R and B is ordered by the relation S. And you can rewatch Lesson 10 if you want a refresher on orderings. Then, an isomorphism from AR to BS is a one-to-one function f from A to B, such that x, r, y, if and only if f of x, s, f of y. To illustrate, let's look at two super simple sets, the sets 1, 3, 5 and 2, 4, 6, ordered on the regular ordering less than. We can draw these sets as lines like this, and for these two sets to be isomorphic, there must be a function that not only maps each element in 1, 3, 5 to an element in 2, 4, 6, that would be equinumerosity, but which maps these elements together in order. That is, the function that maps 1 to 2, 3 to 4, and 5 to 6. A function that maps 1 to 4, 3 to 6, and 5 to 2, for example, is not an isomorphism, because 3 is less than 5, but f of 3 or 6 is not less than f of 5 or 2. It turns out that for practical uses, while equinumerous sets don't always intuitively seem to be or look similar, isomorphic structures pretty much always look the same. If we then go back to our n and z example, we can now see why the natural numbers and the integers are not isomorphic, even though they are equinumerous. The natural numbers only go in one direction, but the integers go in both directions. You can't come up with a function that maps elements of these two sets in order, because the order of the integers goes on for way longer than the order of the naturals. You actually need two sets of natural numbers to form an isomorphism, one to go forward and one to go backward. Therefore, the ordinal number of a structure is a set that is isomorphic to that structure, sort of. The reason I say sort of is because the actual definition of an ordinal number involves something called the epsilon image, which I didn't feel was super important for this conceptual video, but which involves a lot of technical stuff that is very important for actually defining what ordinals are. So sorry for misleading you a bit, but we're going to go through a bit of a softer definition that explains more of how ordinals actually work. So we define the first ordinal number to be 0. Simple enough. From there are two ways that we can construct another ordinal number. The first way is by simply adding 1, and it's a little more complicated than you'd think. So recall from Lesson 6 that we defined 0 as the empty set, and every natural number after 0 as the set of all the natural numbers before it. So 1 equals the set of the empty set, 2 equals the set of the empty set and the set of the empty set, and so on. In general, if you recall from Lesson 1, n plus 1 equals n union the power set of n, for any natural number n. We keep adding 1 forever and ever and ever, and reach higher and higher natural numbers. But we can only get so many values by adding 1 to 0. So the other way of constructing ordinal numbers is by taking the union of any other set of ordinal numbers. Recall, again, from Lesson 1, that we constructed the first infinite number by taking the union of all the natural numbers. We called this least infinity omega. Omega is actually the ordinal number of the natural numbers. It's the infinity that you get if you go the teeny tiniest bit past the greatest finite number that you can think of. Now we've given ourselves a fresh start, so we can start adding 1 again, using the same rule from before. Omega plus 1 equals omega union the power set of omega, and so on and so forth. We can do this forever and ever and ever until we've added all of the natural numbers, and we have to union everything again to get omega plus omega, or 2 omega. Imagine that we've now added omega infinity times, and we're ready to take the union of the whole thing again. Well, we've now reached omega times omega, and that would be omega squared. So as you can see, we can continue this process of adding and unioning forever and ever and ever to get every single ordinal number, or size classification, of not only finite but also infinite sets. That was a lot, so let's close out by applying this idea to some familiar sets. We've already said that the ordinal number of the natural numbers is omega. Well, what about the integers? We can get the non-negative integers with the set omega, but we still have to go in the other direction. So we add 1 to omega to include the integer -1, then we add 1 again to include the integer -2, and we do this omega times all the way to negative infinity. So the size of the integers, as we showed before, would be 2 omega. We can do the same thing for something like the coordinate plane. We will start with 2 omega for the x-axis, and for each of these 2 omega x coordinates, there's a corresponding 2 omega y coordinates because the y coordinate can be any integer. So the ordinal type of the coordinate plane is 2 omega times 2 omega, or 4 omega squared. As you can see, ordinals finally allow us to achieve one of the major goals of set theory, which is to treat values of infinity and infinite sets as if they're just another type of numbers. We can determine their size and do arithmetic with them, similarly to how we would with finite numbers. And that concludes the 11th and final video of this video series about set theory. I hope you enjoyed watching this video series as much as I enjoyed making it. Bye!